Now we're going to look at calculus with Euler's number, which is particularly interesting. It has a particularly interesting property, which is kind of cool, so we'll investigate that. And remembering that it is pronounced Euler, not Euler, even though it does look like Euler. Okay, because you will annoy your maths teacher if you say Euler. And it's never good to annoy the person who's marking your exams. Alright, so let's dive straight in. A bit too far there. Okay, so Euler's number has this really nifty property when it comes to differentiating, and what that is that the derivative of e to the power of x is just itself. So if you were to differentiate e to the power of x, you would get e to the power of x, and if you keep doing that, you will always get e to the power of x. Okay, which makes calculus with Euler's number quite straightforward. So we'll have a quick look at how this comes about. Alright, so the proof involves investigating this limit. Alright, we're going to look at the limit as h tends towards 0 of a to the h minus 1 over h. Okay, and we're looking at values of a being greater than 0. So you might be thinking, well, how on earth did we get to that? So let's have a look. We're going to say, so we're forgetting about Euler's number for the moment, we're just talking about an exponential. So we've got this function, f of x equals a to the x. Now, we know from our limit, differentiating by first principles, if we want to differentiate that, we can say the derivative is the limit as h tends towards 0 of a to the x plus h, that's our f of x plus h, minus a to the power of x, which is our f of x, over h. Okay, so remember what we did when we went and looked at the secant method, limiting chord theorem, when we're trying to limit this distance between 2 points on a curve to 0. Now, because we've got this a to the x here, remember we can write, when we've got a power, we can write this as a to the x times a to the h. Okay, and what we've then got there is this common factor a to the x here and a to the x here, which we can actually take outside the limit. So we can put a to the x outside the limit, and then we've still got our limit as h tends towards 0 of what's left, which is a to the h minus 1, because we factorised that out, over h, which is where this limit comes from. Okay, so the course notes on the syllabus say that you need to be able to do some investigating into this limit and having a look at the properties or particular properties of different numbers for different values of a. So the reason that we're looking at this is, what if we could find a value such that this part, this limit, equaled 1, and therefore the derivative would just be itself, a to the x times 1. So if this whole limit can equal 1, then the derivative of a to the x is just a to the x. So that's what we're going to do. So the easiest way to do this is actually with a spreadsheet. Now you can either use Excel or something similar, or you can do it on your class pad. And I'm going to show you how to do it on your class pad, because it is quite useful to know how to muck around with spreadsheets. Okay, so the first thing I'm going to do is just type in a couple of variables. So I'm going to say I'm going to set a, and I'm just going to start that as 2. Okay, we'll just see what that is. H, now we want h to be a really small number, so we can make it something like that. Okay, and the limit is going to be, and now we use equals, so you should be able to see I'm typing, oops, where are we? There we go, typing down here, so that whatever I type in here goes in the cell. So the limit is going to be our a, which is this value up here. So that comes up as b1, a to the power of h, which is this value over here. And we do want to put some brackets around there. Whoops. So put a bracket in there. And we can go minus 1, divided by, and we're dividing by h, dividing by h. Okay, so there you can see we've got a limit. So the limit, if a is 2, the limit is 0.69, and we're trying to get this number to be 1. We want that number to be 1, so that's a little bit lower than 1. Alright, so let's see what happens if we increase this. Let's say we'll increase it to 3. Okay, now you can see the limit has changed, but it's now up over 1. It's 1.098, so we know it needs to be a little bit less than that. So maybe we try 2.9. Okay, so it's coming down, maybe 2.8. Still a little bit high, 2.7. Oh, now we're a little bit low. Okay, so we know it's between 2.7 and 2.8. 2.71. It's looking pretty good. 2.72. A little bit high. Okay, so 2.715. Okay, so I hope you can sort of see where we're going with this. 2.716. That's pretty good. 2.717. Alright, getting closer and closer. Alright. And what you should be able to see is that we are actually approaching Euler's number. Okay, so as we're using the technology on this to do our limit, and of course you can do this with iterative formulas and things and do a little more sophisticated way, like a sort of goal seek, but this is sufficient to show what we're doing. We're getting this number here such that the limit is as close to 1 as possible. Okay, so what you end up with there is when you use your spreadsheet to investigate, you'll find that for the limit of this one over h, for that to equal 1, a equals e, Euler's number. Okay, and therefore the derivative of Euler's number e to the x is just itself. So that's the proof that you need to sort of be aware of with that one. Okay, so what about e to the kx? Because we're not always just going to have e to the x. We might have some number in front of the x. So how are we going to deal with this one? So what we can do is use the chain rule, and we can say let u equal kx. Okay, then you have y equals e to the power of u. Okay, and remembering our chain rule, we're going dy dx is dy du times du dx. Okay, so differentiating this with respect to u is just itself. Alright, and differentiating this is just going to be k. Alright, because the derivative of kx, where x is your variable, is just k, and now substituting kx back in here, that gives you k times e to the kx. Okay, so when you have something up here, a constant in front of the x, differentiate that function, bring the derivative down, and then leave this e to the kx, so leave that untouched. Okay, so to generalize, what we can say is that if you've got h of x equals e to the power of some function of x, then the chain rule gives the derivative of that function. So whatever e is to the power of, differentiate that, bring that down the front, and then multiply by the unchanged function e to the f of x. So let's do a couple of examples, because that's the best way to sort of get this stuff cemented into your head. Alright, so the first one here, we've got if y is e to the 3x, okay, we know that the derivative is going to be the derivative of this, which is just 3, times the original function, e to the 3x. Okay, so really straightforward for these ones. For b, we've got y is e to the negative 2x. So likewise, the derivative of the index up there is minus 2, and then that is unchanged, e to the negative 2x. Okay, and with a question like this, you just need to be wary, if it was in the test or an exam, if the question said to express it with a positive index, in which case you need to bring that down. But if the question is written as a negative, then you're fairly safe to leave it as a negative unless specified otherwise. Alright, let's have a look at C. So this one's a little bit different, but same deal applies. We want to differentiate the index. Now the derivative of 2x plus 1 is just 2 e to the 2x plus 1. Okay, not any harder. Alright, and the last one for D, so I'm going to rewrite this. It's a little bit easier to see. It's e to the negative 2x plus e to the 3x. Okay, and you just deal with these separately. So what we're looking at is the derivative of that, negative 2 e to the negative 2x, plus, and over here the derivative of this is 3 e to the 3x, so it's just a combination of parts A and B. And because the question was written as a fraction with positive indices, we're going to write the answer in the same fashion. So as a rule of thumb, write your answer in the form the question was written in, 3 e to the 3x. Okay, so that will give you your answer there. Alright, a couple more. Not too much more complicated. Same deal applies. Okay, it's just now that maybe the differentiation in the index is a little slightly more complicated, a little more unusual. So we've got y is e to the x squared, but it's exactly the same thing. When we differentiate, we're going to differentiate the index. So the derivative of x squared is 2x, so that gives us 2x, and then multiply by the original function, e to the x squared. Okay, and then b, same thing. So y is e to the x squared plus 4x. Alright, so the derivative differentiate that, which is 2x plus 4, and then multiply. So the only thing here is to make sure that you put that first derivative, this part, in brackets, because of course if you don't put that in brackets, all you're multiplying this by is the 4, and you'll end up with the wrong answer there. So making sure that you're multiplying the whole of this function by the derivative of the index there. So use your brackets. Okay, and the last example here says, for each of the following, find the derivative with respect to x and then evaluate at x equals 2. Given that, sorry, it's cut off a little bit at the edge there. Given that when f of 2 equals 0, so f of 2 equals 0, f prime of 2 is 4, and f prime of e squared equals 5. Now, you're probably looking at a question like this and think, what does that mean? But have faith, work through it, and you'll find that these values come in handy. Okay, so let's start with the first one. We've got a, so y is e to the f of x. Now, we know that the derivative of that is just going to be the derivative of this, and we don't know what that is yet, but we know that's f prime x times e to the power of f of x. Okay, so that's the first bit. Now, when x equals 2, okay, suddenly this is more helpful. So we want y prime, and we want f prime at 2, e to the function at 2. Okay, so what we've got there is, here we go. So we know f prime 2 is 4. We know that f of 2 is 0 from here. So we've got 4 times e to the 0. Of course, anything to the power of 0 is 1. So therefore, it equals 4. So when x is 2, the derivative or the gradient is 4. And then we do the same thing over this side. So we've got y is the function e to the x. Okay, now this one, we're looking at a chain rule. So what we have here is a composite function, where we've got that nested function. So we've got some function of e to the x. Remembering our chain rule means that we need to differentiate the function as though this was just x. So we're basically looking at f prime of e to the x, and then we differentiate the function in here. And of course we know now that the derivative of e to the x is just e to the x. Okay, doing the same thing when x equals 2. We know that the derivative, oops, that should be y prime. The derivative is there, e to the power of 2 times e to the power of 2. Okay, and we've been told up here that the derivative at e squared is 5. So this part's going to be 5 times e squared. And that gives you your value of the gradient at x equals 2 for this function here. So that's really all there is to it for calculus with Euler's number, at least to start with. So the basic thing to remember is that the derivative of e to the x is itself. This is really handy. And we can use the chain rule to show that if you've got h of x is e to the power of f of x, then you just differentiate the index, bring that down the front, using brackets if necessary, and then multiply by the original function. So I hope what you're sort of seeing here is that the use of the chain rule is really quite important. Often, if you've got a function that looks a little bit complicated, you can use the chain rule to help you get through that, and quite a lot of the proofs sort of going from here use the chain rule. So make sure that you've really nailed that, to make sure that you're staying on top of everything.